Okay, so let's go ahead and get started. The first thing we need to learn about to understand the math behind quantum computing is the idea of the vector. While it might sound complicated, a vector is really just a list of ordered numbers. We usually write vectors vertically with square brackets around the numbers so they look something like this. Every entry or number in the vector is called a component of the vector. So for example, the vector 1, 0 would have two components, a 1 and a 0. The number of components that a vector has is called the dimension of the vector. So this vector would have a dimension of 2. There are lots of different ways to write vectors depending on the use, and sometimes you can see vectors written horizontally or with angled brackets, but for this course we'll mostly be sticking to the vertical representation. So now that we understand the basic ideas of the vector, we can move on to thinking about vectors graphically, and we can do this by graphing them on a plane.
So as an example, let's just start off with a standard xy plane and try to graph a simple vector, say 2, 1. Then we would start off pretty similarly to graphing a point in space. So we go 2 in the x direction and 1 in the y direction to get to the point 2, 1. Unlike points though, we usually draw vectors as arrows, with the start of the arrow or the tail at the origin, in this case which is 0, 0, and then the end of the arrow or the tip of the arrow at whatever point is described by the vector. So in this case 2, 1. Okay, and let's do another quick example. This time, let's try maybe -1, 3. So we first have to start off by getting to the point -1, 3, which is here, and then we can draw the vector itself. But we can actually do even more with vectors, including addition and subtraction, and it's actually really simple. We can add vectors together by adding each of their components together one by one. So let's say, for example, I wanted to add together the vectors 2, 1, and 1, 1. The first step would be to draw them next to each other like this, and then we want to go component by component. So now we have 2 plus 1 equals 3, which means that our final vector should have a top component of 3, and we know that 1 plus 1 is 2, so the bottom component should be 2, which means that our final vector here is 3, 2. And let's also quickly try an example with subtraction. So say we start off with the vector 5, 4, and then we want to subtract 3, 2. Then we again write them side by side like this, and then we go component by component. 5 minus 3 is 2, and 4 minus 2 is also 2, so our result is 2, 2. One quick note here is that if we want to do addition or subtraction with vectors, we need the vectors to have the same dimension. Otherwise, the components won't match up and the math gets completely messed up. So for example, if I wanted to do 5, 4, 3 minus 2, 4, then we would try to write it out, but there's always one component which gets left out. Okay, and finally for this part of the video, let's cover how to graph the sums and differences of vectors. As an example, let's try the sum 1, 2 plus 2, 1. The way we graph these vectors together is by taking the first vector, which is in this case 1, 2, and graphing that like we did earlier. So this part is pretty simple. But for the next vector, what we have to do is we have to start the vector at the tip of the first vector and then graph it, instead of starting at the origin. And the arrow from the origin to the tip of the second vector will actually be our sum vector. The next thing we can do with vectors is multiplication with regular numbers, which we refer to as scalars. So for example, the number 1 or 5 or pi would be an example of a scalar because it just doesn't have any components. It's just a normal number. So let's pick a scalar, let's say 2 in this case, and let's then pick a vector, say 2, 1. Then if we wanted to do 2 times 2, 1, we would first do 2 times 2, or we would multiply 2 by our first component, and then 2 times 1, which is 2 times our second component, which would give us 4, 2. And the idea of multiplication with vectors is the same as with normal numbers. Multiplication is still just repeated addition, which means that we could also rewrite this example as 2, 1 plus 2, 1. And if we wanted to graph this, we would basically just be drawing the same vector over and over again, however many times we need it to multiply by, which also makes a lot of sense. Alright, so now let's take a quick break for some practice problems, and then we'll get back to some other fun stuff we can do with vectors. Okay, and the final topic of this video is the magnitude of a vector, which is basically the length of the vector. So let's say we have the vector 3, 4, and let's actually go ahead and graph it. Then one thing we notice here is that we can actually make a right triangle if we draw these two lines. And now to find the length of this vector, we can use the Pythagorean theorem. We know that the horizontal side here should have a length of 4 since we start at 0 and go to 4, I know that the vertical side should have a length of 3, since we start at 0 and go up to 3. So if we say that the length of the vector is x, then we know that x squared equals 3 squared plus 4 squared, so x squared is 25, meaning that x is 5. Typically, we write the magnitude of a vector by putting 2 bars around it. So for example, if our vector v was equal to 3, 4, then the magnitude of v, which could be written like this, would be equal to 5. And this notation is pretty similar to the absolute value notation, so make sure to not get these two confused. In fact, a lot of textbooks and other resources even put 2 bars around the vectors like this to make it easier to distinguish. So now we know how to find the magnitude of a 2-dimensional vector, but what about a 3 or 4 or even 10-dimensional vector? Luckily, there's a nice generalization we can use here. So given some n-dimensional vector, let's just write it as a equals a1, a2, a3, all the way up to an minus 1 and then an. The magnitude of this vector is the square root of the sum of all the squares of the components. So it would be the square root of a1 squared plus a2 squared plus ... all the way up to an squared. One easy way to remember this is to just think of the Pythagorean theorem, but with a lot of other terms under the square root. All right, and to end off this lesson, let's just do a quick practice problem using all of the topics we've learned so far. So given these two vectors a and b here, we have to find the magnitude of a plus b. If you want to give this problem a try, then please pause the video and try it yourself. Okay, so let's go ahead and start the solution. First, let's add the vectors a and b to get the sum vector. So we have 1 plus 7 equals 8 for the top component, then 2 plus 1 equals 3, 3 plus 1 equals 4, and 7 plus 7 equals 14. So our sum vector should be 8, 3, 4, and 14. Now let's find the magnitude of this sum vector. We can use the formula we learned earlier. So let's get the square root of all the squares of the components. So that should be square root of 8 squared plus 3 squared plus 4 squared plus 14 squared. And from here, it's just some simplification. So this is equal to the square root of 64 plus 9 plus 16 plus 196. And if you add all this up, you get 225. So your final result should be the square root of 225, which simplifies to 15. So the magnitude of the vectors a plus b is 15.